let us start this lecture with a thought process from Sir Cyril Norman Hinsel Wood, who says that nobody, I suppose, could devote many years to the study of chemical kinetics without being deeply conscious of the fascination of time and change. This is something that goes outside science into poetry, but science, the subject to the rigid necessity of always seeking closer approximation to the truth, itself contains many poetical elements. So, basically he is talking about it is an approximation what you are doing in chemical kinetics, and it is approximate to the truth, it is not the truth. Okay. So, anyway, we are discussing basically about chemical kinetics, and in the last lecture I initiated discussion on collision theory. The collision will be taking place between molecules and even atoms and radicals, right, because these are all moving in a random motion, right. And even if there is a collision between molecule and another molecule or a radical, then need not to go to the chemical reaction, isn't it? Will it go to chemical reactions? Not always. I will just take one example just to say that why it is not so. Let us say that this is the reaction CH4 is reacting with OH going to CS3 plus water, right. If I take the structure C here, let us say H here, right, I will take, let us say it is reacting with like OH, because this methane molecule is colliding with OH, right. OH I can have a like this, let us say OH is moving towards that, right. Now, will it be any if it is, this is the OH and of course, this is your CH4. Now, with this H, this is going and colliding, right. If it is colliding, is it leading to the formation of CS3 and water? Certainly no, this is basically no reaction, right, because each H are similar in nature, naturally it will be not doing that. But however, if I take the same example and if it is HO the molecule and it is colliding with here, then it will lead to the reaction, right, yes or no. So, this is taken care by what you call a orientation, right, or you can say geometrically, because how it is getting into, and that is a similar thing. We meet several people, but we may not have a good bond, right. Okay. That depends on the compatibility is important in our relationship. So, that is taken care by a steric factor, what we had discussed in the last lecture. And even if it is oriented properly and it is colliding, right, of course, the reaction may take place, but we need to look at that it should have enough energy to break a bond and form a new bond, and that energy we call it as a activation energy. Okay. And we have talked about activated complex, leading to that I will be discussing little later on. And if you look at, and what is the probability of that? That probability of having certain activation energy, right, leading to a collision, what we have looked at is basically probability of reaction, you can say, is what, E power to the E by RUT. This is one factor, and if you compare to your Maxwell function, this is similar terms are there, and into steric factor, and this is your steric factor. But why we are talking about it? Why you are talking about it? Because our interest to find out a relationship for the specific reaction rate. For example, if I take the A molecule is reacting with B going to the product C and D, I want to find out the change of concentration of A with respect to time, and keep in mind this is getting consumed, therefore, it will be negative, is equal to K. If I say this is forward reaction rate K, then C A and C B. Now, our objective is to find out the K is the specific reaction rate, and sometime reaction rate coefficient we call, right. That is the main objective, and if I know this, then only I can find out how much concentration of A is changing with respect to time. Now, this will be invoking basically collision theory and then find it out. Let us, what is that? If I look at from the collision theory of point of view, like dCA by dt is nothing but what you call number of collision between molecules A and B, right, per unit volume and per unit time. And then what is the, because not that all collision will be leading to the reaction, there is a probability of successful collision leading to reactions. Successful means that, but I am just writing for the clarity. Successful collision means for this case it is only two reactions, right, otherwise it is not successful. Then kilomole of molecule A per number of molecules, A molecules, I can say A molecules, right. Now, if I can say this is basically, if you look at number of collisions per unit time, means what? Collision frequency, right. That I can write down dCA by dt is equal to ZAB by volume, and ZAB is basically collision frequency, right, into what is that? Probability, we know that is E by RUT into steric factor into this is kilomoles of A per number of molecules, A molecules, right. What is that? That is nothing but your Avogadro's number, yes or no? Kilomoles like per the number of molecules, that is nothing but Avogadro's number. So, if you look at, now we will have to find out basically collision frequency. For that we will have to go to what you call our molecular theory of gases and find out the what we did earlier, right, similar way, right. Let us now evaluate collision frequency. So, let us take a simple collision, right. Let us consider simple collision in which molecule A is reacting with another molecule, right, with the same diameter, right. Let us consider simple molecules, right, and let us consider simple collision event. In this event, what is happening? The molecule A, let us say the molecule A, which is moving at a velocity v, right, average velocity, and it is colliding with another molecules of same diameter. Keep in mind, this is d sigma and this is also sigma. Sigma is the diameter of the molecule, right. Sigma is the diameter of molecule A, right. Now, when their collision will occur? Only when, if you look at when it can happen the collision, provided they are of course touching each other, and this diameter will be basically sigma. The center to center distance between two molecules when they are in touch with each other, like they are touching each other, will be sigma, then only. If it is more, collision will not occur, right. Now, we will consider, let us say a case, let us say there is a molecule here and it is moving, right, this way, right, and there is some other molecule which is similar diameter, but this is fixed. Fixed means is not moving, right. Let us say there is a molecule here which is fixed and this molecule has reached here and it has gone with a velocity v average, and this is collision occurring here. So, this diameter, if you look at this diameter is what? This is 2 sigma. This is moving and this is a fixed molecule. We are imagining this, not that way, we will go slowly and just to simplify I am talking about it. Now, I want to find out collision frequency, right. Collision frequency I can say ZAA is equal to what will be? Number density, right. We know this is number density. What is that? Number of molecules A divided by unit volume, right, that is N, into, if you look at what is this, this is basically I can say, all right, I can write down A divided by volume, right, into, because I want to find out frequency. So, what I will do? There will be collisions, right, that will be basically the swept volume with which the molecules are moving and colliding. Let us say this is between the two mean what you call between two collisions, and that distance we call it as a mean free path, right, average distance. And the swept volume between two collisions, right, or this thing will be what? Will be pi by 4 to sigma square, right, into average velocity, yes or no. So, that happens to be, if I look at this, ZAA will be N naught A by V. V is the volume, okay. Keep in mind this is volume, okay, and this is average velocity, right, and this is of course number of molecules A, right, this is number of A molecules. Anything I am missing? Sigma is the diameter of the molecule, right, into pi sigma square V dash. Now, keep in mind that this in actual case all molecules will be moving, it is not that fixed, it will be moving, that molecule this one and this one will be moving, right. Then what will be the average velocity then? If it happens to the same average velocity, then it will be root 2, yes or no? Yes or no? Average velocity will be root 2 V dash. So, for actual right, gas in which the molecule moving, assuming of course the Maxwell relationship, velocity distribution ZAA will be n naught A by V pi sigma square root over V dash, right. But keep in mind that here what we have assumed, all molecules are having same diameter, but actually it is not. Let us say that there is a molecule A in this example, there is a molecule B in this example, okay, because I am saying that A is reacting with B. So, therefore, the A molecules and B molecules are colliding, right. And when this collision will take place? Only when the sigma A plus sigma B divided by 2 will be the diameter, right, then only. For example, if I say this is A, right, this is B, and then sigma AB, this will be sigma AB will be sigma A plus sigma B divided by 2, then only collision will occur, otherwise no, because if it is far away it will not occur, right. Sum of the diameter of A and B divided by 2, that is the average diameter, right, that distance should be maintained. Now, if you look at then collision of A molecule with all B molecules, right, that will be, I can say ZAB will be equal to what, root 2 into NB, and this NB is what, N naught B divided by volume, okay. NB is nothing but N naught B divided by volume, yes or no, this is number density of the molecule B into pi sigma AB square into VA, right, right. But what we want is basically the collisions of molecule of all A molecules with all B molecules, not a molecule A only, like not a single molecule of A, okay. And what will be that? That will be basically total collision per unit volume, right, that is total collision per unit volume, right, per unit time, that means during which all A molecules is reacting with B molecules, right, not that only A molecule is reacting with all B molecules. That will be ZAB by volume will be equal to what you call like with equal to what is that? This is collision frequency of A with B, with all B, into number of molecules per this divided by V, right. That means this is basically N naught B by V pi sigma AB square into VAB average into N naught A by V. So, what is sigma AB? Where sigma AB, what will be sigma AB? That we have already seen, that is sigma A plus sigma B divided by 2. What is VAB? From the kinetic theory of gases, right, we know that will be 8 kb T divided by relative mass. What is relative mass? is nothing but mass of A, mass of B divided by mass A plus mass B, right. So, I can write down here, right, is equal to ZAB by V is nothing but NOA by V into NOB by V into pi sigma AB square, right, into VAB would be what, 8 KB T by MR, right, okay. And keep in mind that this V average AB will be nothing but root over V A square average plus VB square average, like that is the meaning of that, right. And this we are getting basically from the molecular theory of gases. Keep in mind that what is this NOA? NOA will be what? Can I say this is nothing but your V is equal to, what is NOA? NOA is nothing but Na into An divided by V, yes or no? Because number of molecules is equal to, we know as Na is equal to NOA divided by An. An is your Avogadro's number. This is Avogadro number. Yes or no? Number of molecules divided by number of molecules per unit, this thing, mole, right. So, that means this number of molecule cancel out, nothing but mole, yes or no. So, now what is this one? What is this one? Concentration, right, that is nothing but CaAn. Similarly, NOB by B will be CBAn. So, I can write down, right, ZAB is equal to CaAn and CBAn pi sigma AB square 8 KB by T MR. This is relative, not I think okay, relative mass half. So, keep in mind that this is the collision frequency per unit volume, okay, there will be unit volume, and this is basically provides reasonable good values for a bimolecular reaction. But however, if you look at like trimolecular reactions which is likely to occur, the error will be very much, it will be order of something 10 power to 6, right. Therefore, that is the limitation of these kind of things, therefore, one has to look at it, right, and we will have to rely on the experimental values. I will be coming to that little later on. Now, what we will do? Now, we will use that thing and then find out a relation for reaction rate, right. Let us say this is equation 2, I think I had not told, let me get into here, this is equation 1, right. This is equation 1 I am saying. I will be using this equation now, right. So, by clubbing equation 1 with equation 2, or I could have, we can have, so what I will get, dCA by dt is nothing but CA AN CB AN pi sigma AB whole square 8 KB T by MR into e power to the RUT into S into 1 by AN, this an will cancel it out. So, what you will get? You will get dCA by dt is equal to Ca Cb an pi sigma ab square 8 kBt by mr E by RUT into S. I am putting S here. Okay. This is your steric factor, and keep in mind that E by RUT is a non-dimensional parameter. So, also the steric factor, that means steric factor is also a non-dimensional parameter. And if I consider this portion, right, these are basically, you can say it as a what you call constant, right. Now, if I will write down, this is your, let us say, equation 3, and then I will write down the what we had done, like from the simple in terms of the specific reaction constant, that is dCA by dt is equal to K Ca and Cb, right. Let us say this I am saying right now 4. Now, if I compare this 3 and 4, what I am getting? I can write down this as A, right. A is the pre-exponential factor, I am saying. That means K, if you look at, I can write down what is K then? A RUT. That means we got a relationship, and this is your exponential factor. This portion e power to the is exponential fraction. Okay, I can say this is exponential factor, and keep in mind that this is depend on the temperature, and E is the activation energy, and A is your pre-exponential factor. So, with this we will stop over here, and we will be discussing more about this specific reaction rate which we have derived from the molecular theory or the considering the collision theory, right. So, thank you very much.